So this one is problem F, and I guess I call it the skier. And it says, a skier starts from rest at the top of the hill. The skier coasts down the hill and up. Second hill, as the drawing illustrates, the crest of the second hill is circular with a radius of r equals 36 meters. Neglect friction and air resistance. What must be the height h of the first hill so that the skier just loses contact with the snow at the crest of the second hill? Okay, let's just write in numbers. That this one here, I think it's at r equals 36 meters. And at this time the drawing is so small, so this was supposed to be an R. Okay, I'll try this again. Let's try to make a clean R here. There we go. Okay, notice that this is totally out of scale because 36 meters is 100 feet or so. But again, they want to squeeze it into they want to squeeze it into this drawing. Okay, let's see. It says a skier starts from rest. That means that the velocity of the skier over here has to be v0 equals 0 meters per second. Then the skier coasts down the hill and up a second hill, as the drawing illustrates. That probably means that we need two parts. So we need a part over here and a part over there. And that actually overall means that the problem becomes quite mathematically involved, so that I actually assign it as a conceptual problem, because the physics is more important here than the math. But towards the end here of this problem, I will actually go through the math. But let's look at the physics first. So here the skier starts at 0, but of course he or she, let's call it she because all the other skiers here were he's. So she needs just a little bit of a push, but it's so tiny that we just consider it to be that her initial velocity is 0 meters per second. Now, of course, she accelerates here, accelerates more, and then, of course, on the way up here, she is pretty fast, but, of course, here she is losing some speed. We also assume that, just like they say in the problem, no air resistance and friction, and we also assume that she's actually not speeding up, so she only uses her poles and her skis to actually balance herself, so she's not speeding up. So that means as she goes up here, she's losing some speed, but she has appreciable speed that at this point up here, she could actually, as the slope is going down again, she could actually lift off. So that's what it means. Just loses contact with the snow, and that means that she actually starts a little bit flying, just losing contact. That means something now. She's kind of on the brink between staying on the snow and just losing contact. Okay, obviously between here and here we would have energy conservation. So here we have potential energy. So potential energy initial, and then over here we have kinetic energy. And notice that they gave us that zero level line here, the one that I prefer, and that I said, it's arbitrary where you set it, and they set it in such a way that it's convenient. So here this one is the zero level potential energy, and that's where they want to figure out what the height is. Okay, now as I said, this is a two-part problem, so something must happen over here where she just loses contact. What does that mean? Well, what it means is that gravity is trying to pull her down, which means she should sink into the snow, but the support force pushing her up is just holding her up enough that she's going to stay on the snow. However, she just loses contact, and that actually means there is no support force. And that's kind of interesting. So what happens here? Well, I will write down that here is her weight, mass times gravity pulling her down, and so that's her force here, but she is skiing in a circle here, and that reminds us of the centripetal force. So the weight that I have over here equals actually the centripetal force, respectively So I'm going to write here W for the weight, or Fg I guess I will write. So Fg for her gravitational force or her weight. And that actually is the centripetal force, and that actually is then her mass times her velocity squared divided by the radius. See there, that's where the radius comes in. So here I have to go back to the chapter on centripetal force and make the conclusion that, oh, what just loses contact means here is that there is gravity pulling her down, but it's the only force that's acting, and that actually gives her the centripetal force, and if she just loses contact, then she would be actually in free fall afterwards, and there is no support force in this one here. So from a physics point of view, this is how we would be actually done with it, that here, from here to here, we have energy conservation, potential energy over here equals kinetic energy over here, and then in the second part, she is in the circle here, we have that the force pulls her down, and that is actually the centripetal, the weight pulls her down, that is actually the centripetal force, which is expressed as such. So as I said, for the physics we would be done, but as I said, I'll do the math as well. So what I have is the initial potential energy equals final kinetic energy. Oh yeah, and then before I actually get started, what I should do is that this is what they're asking for, that height h there, gravity is always given, mass apparently will divide out. The final velocity over here, we don't know that. This should be actually the VF. But we don't know that at this point, and we could calculate it. The V0 is given, that is 0, and from that we should be able to figure out what h is. Okay, so mass, gravity, height equals 1/2 mass velocity squared, and h therefore equals, mass cancels out, v squared, vf squared divided by 2g. That means we need vf, and I basically wrote this over here. So centripetal force would therefore be, oh, my handwriting is pretty bad here, this was supposed to be centripetal, that on the left hand side all I have is the weight for the centripetal force, and that equals the mass times acceleration, and the centripetal acceleration is being expressed as velocity squared over the radius. Again, mass cancels out, and then I can go in here, and actually this is kind of convenient, because what's going to happen now is that I draw myself a fraction bar to g, and then I will substitute for the vf squared, which of course is gr. And after all this algebra, it's kind of interesting to see here the g cancels out, that the overall result is the radius divided by 2, so I'm going to come up with 18 meters for the height. And again, this one here is definitely not to scale. 18 meters is about 10 times as much as what she is tall, so again, it's totally out of scale. And as a reminder to me, what's more important is, besides more important than the math, is the physics here. Potential energy equals kinetic energy, and then here the centripetal force being supplied by the weight, and that then equals mass times the centripetal acceleration.